Hello GGS300, welcome back again to what is going to be the 8th lecture for this class this term, so for quantitative methods for spatial sciences. Today what we're going to be going over is essentially inferential statistics and hypothesis testing. So before I begin, I just want to say very well done on the midterm exam. There were some great scores there, so well done for putting effort into that and performing well. Today we're going to be setting what essentially is the 6th assignment, and that's going to be due 7 days from today, so March the 26th, and essentially that's just going to be building off the work that we're going to be covering today within this lecture at a relatively high level, and then within the laboratory session where we work through some of those examples with some code in order to produce some results which support basically the material that we've covered today. Okay, great. Reach out to me if you've got any queries. It's been nice to hear from some of you, and I'll look forward to hearing from many more of you if you have any further questions. So we're going to be going over the inferential statistics part of the module, so starting to build more into that content. So last week we covered estimation and sampling, confidence intervals, and we're going to be putting some of that into practice today, actually, in order to actually formally test hypotheses. So you'll remember that within this course, essentially what we did in the first third of the course was over here, where we essentially were looking at descriptive statistics, so essentially identifying problems that we have, developing questions around those problems, so maybe trying to understand something about the world, why a process works in a particular way, collecting data, and then basically describing that data based on different metrics that we can use, either single point metrics like the mean or the range, or perhaps thinking about the level of variation within the data, such as the standard deviation, or more broadly looking at the shape of the distribution, so the type of kurtosis that we might have across the whole range of data that we've collected. But there's obviously some kind of limitations there. It's a bit kind of, I think some people might describe it as hand-wavy. It's perhaps not as formal as some of those other statistical methods that we might be able to use, which we're going to be, for example, covering today, so formal hypothesis testing. So perhaps we might have reached some conclusions from that initial tranche of data analysis that we carried out. And then essentially we formulate a set of hypotheses that we want to test, and that's essentially what we'll be covering today. So we might collect some data, prepare the data for analysis, we'll test it using inferential approaches, and then we'll basically evaluate the results, make some judgments based on that, and that can either feed back into further academic development of the model or of a theory, or we can ideally gain some real-world impact out of this stuff. You know, that's where all the magic happens. Okay, so let's not dither too long on kind of that overall perspective of what we're covering and where we're going. Let's focus now on actually getting into the process of testing different hypotheses. So before we begin, hypothesis testing is just one method that we have within the different statistical inference landscape. Remember, we need to understand exactly what a hypothesis is. So we've spoken about this in relatively general terms in the previous lectures that we've been over this material. Remember, it's basically a statement that either needs to be verified or shown to be false, but we're able to use a hypothesis in a way to actually link it into the statistical tests which are available to us in order for us to learn something about the world based on data. So it's a fundamental way that we carry out scientific research, okay? So hypothesis testing uses sample statistics, so that means that we might not have all of the data for an entire population, so we're going to go out and we're going to collect a sample based on some standardized way in which we can collect the data, for example, using some sort of sampling method. And then we can use that to determine whether we have enough evidence to suggest whether a hypothesis is true or not, okay? So, classical hypothesis testing. There are essentially 6 steps, and we're going to go over those 6 steps today. So essentially what we're looking to do is to either accept or reject the hypothesis based on the level of significance that we set prior to actually setting out on collecting data and basically making a judgment about the effectiveness of that data in informing our hypothesis. So this is essentially the alpha value, the level of significance. This is the acceptable error margin that we are happy to have within our data set. So the error, the potential for actually making a type 1 error, as I will explain what that means shortly when we get into this content. This is a binary decision, so you'll remember that we have a probability and then we have a complement, and that when we sum that together we get 1. We are able within that kind of a framework to also affiliate that statistical approach to how we basically either accept or we reject a certain hypothesis that we may make. Okay, so we're going to link those qualitative statements into this kind of probability-based statistical framework so that we're able to say something with certainty about the way that the world works. So those 6 steps, essentially, we're going to state the null and the alternative hypothesis, and I'm going to spend a good bit of time today going over exactly what we mean by that with you. So hopefully by the end of today, you'll know exactly what a null hypothesis is and the alternative hypothesis. We'll then need to actually identify the appropriate statistical test to actually use, and that's a tricky one. It's going to be very easy today, but it gets more and more complicated as you get through the module and you get so many different tests available to you. I mean, it's always the thing that I struggled with when I was just starting out doing this. I'm going to basically show you some tips and tricks in order for you to work out how to do that appropriately. Step 3, you then need to set your level of significance, as we've already discussed. So how confident do you want to be in the results? What's your acceptable error rate for the conclusions that you draw? This is all going to be related to the level of significance that you set, and to a certain degree it's also going to be highly dependent upon the scientific research area that you're operating within. So there are generally schools of thought within each of those scientific areas as to what's acceptable and what isn't acceptable in terms of the level of significance that you use. If you are, of course, using the kind of classical statistics that I'm teaching you here today, there are other types of statistics, more advanced forms, which don't use significance, but we're not getting into that. We're not getting into that in this particular course. I just want to make you aware that this is the kind of very classical statistical approach to how we test hypotheses. Step 4, we would then need to delineate the regions of rejection and non-rejection within our distribution of values to identify where we would accept the alternative hypothesis or basically retain the null hypothesis, so where we don't have enough evidence to reject the null hypothesis. So essentially that can be done using a Z-score, for example, as I'll show you today. And this builds very much off the work that we've carried out before, looking at standardized scores and the number of standard deviations around the mean that can capture a certain percentage of the values, and that gives you some sort of idea about the probability of a value being at one place or another within the distribution. Then we need to actually calculate the test statistics, so I'll do that within this course where we'll get into the formulae. It's actually relatively easy, and it builds very much on the work that we did last week, and it's definitely not as complicated as a couple of the things that we've covered so far. So I think that this should be fairly okay for you. It's just, I think the challenge today is more kind of bringing all of these concepts together, because I've explained before how everything within this module is cumulative. So essentially, the principles that we put together in the first few weeks end up being kind of fairly foundational for then how the other statistical techniques come together. And in fact, by the time we get to the end of this module and we're looking at things like multiple regression, then there's a fairly steep learning curve in terms of how you then fit all of the things together that we've learned this term, from probability through to formal hypothesis testing, and so on and so forth. And then finally, we need to make a decision regarding that null hypothesis that we've set out. So do we basically reject it, or do we not have enough evidence to essentially reject the null hypothesis? So 6 steps. I'm going to cover it now in high level. We're then going to go over some examples of how we do this in the lecture, and then when we actually get into the laboratory work, we'll be taking those examples and basically tapping them out in some fairly simple R code in order for us to show you how you do this in practice. So the step one within this 6-step procedure is essentially to state the null and the alternative hypothesis. So before we begin, let's just think about an example where we might apply this. So let's use an example for a population mean and for a hypothesized sample mean. So those terms might be very abstract to you. You might not really fully understand what that means yet. So I'm going to use this example, which I keep coming back to, which is my kind of standard favorite example for explaining this, which is about whether we have the same house prices in Virginia, the city of Virginia, versus, the city of Fairfax versus the state of Virginia. Okay, so I'm sure as many of you know, Fairfax is it's an up-and-coming area. It's got lots of jobs. House prices are increasing at a very rapid rate, partly due to the good school system as well. And that means that it's very expensive relative to the other parts of Virginia. And as a consequence, we're going to use Fairfax as our sample, and then we're going to use Virginia state as essentially the population. So it's where we're going to be looking at the kind of the mean house price, for example, across the state versus the mean house price that we might get if we just sample some premises within Fairfax. So essentially for the null hypothesis here, we would be saying that there is no difference between the mean house prices in Fairfax versus the rest of Virginia, whereas the alternative hypothesis is indicating that there is actually a significant difference between the house prices, okay? So I think the key part here is that the null hypothesis always hypothesizes that there's no relationship between the processes that we're looking at. So there's no difference essentially between the sample and the mean in this case, the sample mean and the population mean, okay? Whereas the alternative hypothesis is looking for that relationship, okay? So you can see here, we're saying that there is a significant difference between the population and the sample. So let's think now formally about that. So, I mean, I've given you some kind of high-level qualitative description of as to what the null and the alternative is within kind of my house price example. But the key point here is that, especially if you read the chapter in the book, there's very formalized ways for you to understand this. And I didn't want to just start with those quite abstract ways. I wanted to give you some very kind of concrete understanding before we got there. But essentially, if you look in the book, for example, or any other key statistical textbook, your null hypothesis, obviously it's a statistical hypothesis to be tested, but the null hypothesis denoted by H0 essentially says that the population mean, mu here, is equal to the hypothesized sample mean. So the hypothesized mean for the population here, which is mu h. And you can tell that because it's saying that they're equal to each other, okay? And therefore, the complement of that, the opposite, for the alternative hypothesis, is that there is an effect, and as a consequence, the population mean here, mu, is not equal to the hypothesized mean, okay? So you see the equals sign here, it has the diagonal slash. That basically means that it is not equal to, okay? So hopefully you can see that the null hypothesis here has an equal sign and the alternative hypothesis has a sign which indicates that it's not equal. Okay, and that's a kind of very straightforward way to try and understand these two different types of hypotheses. We also, and I didn't really cover this before, have the ability to say whether the alternative hypothesis is directional or not, okay? So if we go back to my standard example for house prices, in our alternative hypothesis, all I have stated is that there is a significant difference, okay, between the sample that we collect and the population, but we don't actually go to the extent of saying that we think that the house prices in Fairfax are actually higher than the rest of the house prices within the state of Virginia. But if we did do that, then that would be the opportunity for us to basically have a directional, one-sided alternative hypothesis. So you can see here that it's directional. We are actually using these operators to indicate whether we think the sample mean here, so the hypothesized mean in this case is larger than the rest of the population. So this would fit well the example that we just discussed. Or in this case here, where we may think that the population mean is larger than the sample mean. So maybe that would fit a different type of problem than the one that we're looking at here. Okay, so that gives you an example of the directional hypotheses. Again, we've covered this non-directional alternative hypothesis before already. Within this example, we have the same nomenclature listed down here as we have up here. Okay, so we're testing whether or not we think the null is true or not. The null is always the baseline. The null is the business as usual. And the null is essentially that there's no difference between, for example, the sample we're collecting and the population. Okay, so I kind of appreciate that it might be more interesting for us to think about those cases where there are effects, and maybe that would be the baseline, but that's generally not how statistics is carried out in this example. The null is the baseline, it's the status quo, it's what we always start with, and we're focusing on whether we should reject that null hypothesis and accept the alternative hypothesis if we have enough information. But generally, the null is always going to be the consistent starting point for us. Okay, well that's step one, and hopefully that's somewhat clear. I mean, there's a good couple of pages in the book which detail those differences between the null hypothesis and the hypothesis, and it kind of writes it in quite basic but lengthy terms. Step two, we need to actually work out the appropriate statistical test. So this is basically going to be chosen by the type of question that's asked and the assumptions that are actually met. So in this case, today we're going to be going over one sample difference of means tests and one sample difference of proportions tests. So it's fairly easy, fairly straightforward. As we go through the next couple of weeks, we'll start to build up to tests which include multiple samples or many samples, such as in ANOVA, analysis of variance, and then we'll start to move on to those other types of tests which look at having many independent variables like multiple regression. But I don't want us to get bogged down in that yet. That's to come in about 3-4 weeks' time. So just focus today on these two different tests. What's really key is actually knowing which assumptions meet your data, and therefore that indicates which test you are able to actually apply to your data. That's the tricky bit. That's the bit that takes a long time to learn, unfortunately. But you'll see the way that I present those tests, there's always a set of requirements. So these are essentially requirements that need to be met for the test to be valid. Okay, so you need to make sure that you're as specific as you can be when you're identifying your tests. So just as one example here, maybe you're going to be saying in your dissertation that you're using a one-tailed, one sample difference of means test, and you've got a large sample, so you're going to be using the Zed statistic. Fine, this is just basically how you end up reporting the test that you've decided to choose. And you just need to be aware that you need to be very explicit about how you report this information in both your assignment, also within any future research that you may do, so that basically the work is reproducible. Okay, so the issue here is that there's been quite a reproducibility crisis in science over the past number of decades, and many high impact publications in the very best journals might not have been able to produce consistent results. So, I mean, how do you know whether it's truth or not? You know, this is a major issue, and therefore you want people to be able to pick up your work, preferably also the code, and actually reproduce the results that you were able to obtain. So transparency and reproducibility is going to be central to how we actually use these tests. Step 3, we need to identify the level of significance. So we need to set an alpha value at the starting point. So this is indicative of the level of error that you're willing to accept. So maybe, for example, if you have an alpha value of 0.05, that means that you've got a 5% chance of this just randomly occurring. It also means that if you obtain a result which meets the alpha value, then you can be 95% certain that this hasn't just occurred by chance. Okay, I hope you managed to pick up there that those two numbers are complementary, the way that we think about them, and hopefully you're going to be able to pick that up as we go through this course, how you're able to think of these statistics in terms of the probability of different potential outcomes. Okay, so I know it's a lot of information to hold on to, but you'll get it hopefully through this course, through the lecture today, also through the laboratory session, and then hopefully you'll be able to convert that into completing your assignment correctly. So the significance level is also known as the likelihood to commit a type 1 error. I'm afraid there's no beating around the bush here. You're just going to have to learn what a type 1 error and a type 2 error is. So a type 1, and you may well be asked this in the tests, the midterm and the final exam, occurs when we basically reject the null hypothesis, but the null hypothesis is actually true. So essentially, this is a false positive. This is us seeing an effect when there isn't really an effect, okay? And whether this is kind of acceptable or not depends on the area in which you're operating. So, for example, maybe this is less of a major issue in spatial sciences. I mean, obviously, it's not great. We never want to be wrong, but maybe the outcome of this may be less serious than in medical sciences, where, for example, if you suspect that someone has perhaps a serious type of cancer, then actually, if you think they have it and they actually don't, but then you subject them to some type of chemotherapy, for example, or some other really quite arduous medical procedures, then that actually could have, a significant impact on their health as well, even if they don't have the original disease that you think they may, and therefore this alpha value will differ depending on the level in which you're operating. So, for example, if we are designing a new shuttle for SpaceX, again, then we might have a different type 1 error margin that's acceptable to us, because obviously if there's a problem with the design, then that could lead to catastrophic effects, right? So this is all going to depend on your willingness to basically accept a false positive or not, okay? So the size of the alpha value that you specify. I think 0.05 is pretty standard. That means you want to be 95% confident that your result hasn't just occurred by chance. We'll also be covering quite a few examples today that use 0.1, so you can be 90% certain that the result that you obtain hasn't just occurred by chance. But it still means, as I described in the previous lecture, that for every 1 out of 10 means, for example, that you might draw in your sample, then there will be 1 instance where it's occurred completely randomly. Okay, so now you can start to see some of the issues with this kind of classical statistical method, in that you've got an element of randomness within it. And if just because you get a significant result, it does not mean that there's certainty that your effect is definitely true. There's always an error at margin, in which case the results could just have occurred by chance. And this is kind of one of those key understanding issues that I'm going to need you to be able to demonstrate to really just show that you've managed to pick up the information this term. Okay, so there's more on this in the book. Type 2 error you also need to be aware of, but that's basically the opposite. So it's where we get a false negative. So that occurs where we don't reject the null hypothesis, but the null hypothesis is actually false. So it's a less serious statistical issue, but obviously we want to make sure that the statistical analysis that we're carrying out is correct at the end of the day. Step 4, we need to delineate the areas of rejection and non-rejection. So remember, go back to what the work that we did before. So we did probability 2 weeks ago, and then last week we did estimation and sampling. All of that work is going to be based on the distribution of values that we obtain, okay? And you remember the fact that we went over some of those key concepts like the central limit theorem last week, and how that enables us to actually sample from a population a set of means, and then actually take the mean of that sample, and how that value that we will obtain, if we meet the criteria for collecting that data correctly, will actually be very, very similar to the population mean. Okay, so it's a very, very strong way for us to be able to obtain data without going away and actually doing a census on the whole population. So you should be familiar with this type of this data distribution now. So a normal distribution here, for example, and we need to basically separate our distribution into the areas where we don't reject the null hypothesis and the areas where we do reject the null hypothesis. Okay, so if we had a non-directional hypothesis, we just said that the house prices in Fairfax are different from the house prices in the state of Virginia, then that would be non-directional, which would mean that our alpha value would be split at the lower end and the upper end of the distribution, because we've not said whether we think the house prices are larger or smaller. We just say they're different, okay? And that means the result could either be larger or smaller. And that kind of contrasts with this other way in which we can formulate directional hypotheses, where we say, actually, no, we have existing knowledge of Fairfax. We suspect the house prices will be larger than the state of Virginia. And as a consequence of that, we're going to use a one-tailed directional hypothesis, and that means that we're only interested in delineating an area of rejection in the upper half of the distribution, okay? Because we suspect that when we sample the properties there, that mean's going to be in this area due to a priori knowledge. So a priori, I've explained before, just means knowledge you know already, essentially. Okay. Great, so the critical value that we need to basically identify using either the Z or the T distributions, depending on how many samples you've got, it basically will separate the zones of rejection and non-rejection, okay? So for the one-tailed, you need to find the Z value, which is associated with that alpha. Here we go, down here, so 1.65 standard deviations above the mean here, in this case. And then also for the two-tailed, find the Z value associated with the alpha value divided by 2. Remember, I explained before that we need to split the effects because it's non-directional in the lower part and the upper part of the distribution, okay? Great. Then in step 5, we need to essentially calculate the test statistics. So this is going to depend on the test which we're using. I'm going to present examples today of how we calculate this, but it's no more complicated than what we've essentially done in previous weeks. But just remember that those test statistics are going to depend upon the type of distribution that we may use. So if we've got below 30 values in our sample, then we're going to be focusing on using a T distribution. But if we've got a much larger sample, so over 30, for example, then we're going to be focusing on using a normal distribution, so we can use the Z statistic, okay? Step 6, this is the more complicated part. We need to bring all of the information together. And then once we've done that, we need to actually work through those steps in order to make a decision regarding the hypotheses that we've stated, okay? So if the calculated test statistic falls in the area of rejection, then we reject the null hypothesis with a confidence level which is 1 minus the alpha value. So if we use an alpha value of 0.05, that's essentially a 5% alpha, then we would have a 95% degree of confidence in this statement that we made, okay? But as the book explains, and as I'm going to explain here, there's a very specific way for us to report our results, okay? So we don't say that we accept the null hypothesis because the null hypothesis is already the status quo. It's essentially the business as usual case. What we do is we basically say that we reject the null hypothesis with 95% confidence, for example, as we're using here. And we conclude that the alternative hypothesis of house prices in Fairfax being significantly different from the state of Virginia is true. Okay, so I'm afraid that this seems long and clunky, but there's a very standardized way for us to make these statements. So if the calculated test statistic does not fall into the area of rejection, then we fail to reject the null hypothesis, okay? So just imagine we're getting mean values from our sample, and if it lands here, which is in the zone where we will not be rejecting the null hypothesis, we can't say for certain that the results haven't just occurred but by chance, okay? So as a consequence, within our accepted confidence level. So as a consequence, we would not reject the null hypothesis if our sample mean, for example, was within this zone here. So maybe this point here, if we're interested in a 95% confidence level, so we've got an alpha value of 0.5, maybe this point here is 1.96 standard deviations above the mean, and the z-value that we get is 1.89. Then as a consequence, in this case, we wouldn't actually reject the null hypothesis, okay? Because obviously this z-value, technically it's below the threshold critical value that we're looking for here, okay? So we'll go over this within the actual laboratory session. Hopefully that will help to clear up exactly the steps that we go through in order to make these decisions. So in that case, we would fail to reject the null hypothesis, okay? So there's insufficient evidence to show that the null hypothesis is false at the 95% confidence level, okay? So, yes, if the calculated statistic that we obtain is larger in magnitude than the critical value, then we would reject the null hypothesis. The null hypothesis is never proven as true. Okay, so this is a lot of information for you to grab hold of. There's multiple steps. I understand it's pretty high level at this point, but please just bear with me because I'm going to work my way through the material and then we're going to go through it in the laboratory session. Hopefully by then, in tandem with reading the book, this information is going to solidify. So let's move on to some examples now. Let's get onto one sample test. So assume we take a single sample. We want to compare a sample statistic to a population parameter to determine if it is similar or different, okay? So often we assume some sort of population parameter using past studies or logic, or maybe we've got actual data. So the examples I've given you so far of house prices within Fairfax City versus Virginia. So if we look at the second example here, thankfully in an age of big data, a lot of the information that we want is already on a computer, so we can actually just extract the mean house prices in Virginia, which are somewhere around $296,604, so around about 300K. And then the question is, well, is the average for Fairfax City significantly different? Okay, so this is one of my favorite examples that I use. We'll also be covering some of these here, so related to the census. So what exactly is the mean household size? Is the average for a hypothetical town in Middletown significantly different from that? Okay. So how do we do this in practice? Because they are just very high-level examples, but we haven't actually crunched the numbers yet to work through exactly what this means. So those are the 6 steps we covered in the previous example. This here is how we actually use one of those particular tests. So we're interested in just comparing a single sample that we've obtained, maybe of house prices, to a population mean overall, okay? And there are certain requirements for that. So you remember that kind of central to this is the central limit theorem. And as a consequence of that, we need to make sure that we have random independent variables. So we need to make sure that we're using random sampling in the sample that we obtain, okay? We also need to make sure that the population is normally distributed. So you remember the normal distribution, it's also called the Gaussian distribution after Gauss, or it's also called the bell-shaped curve. Essentially, that's essentially what we're expecting. In this case, it's an assumption. If your data are not normally distributed and it doesn't meet this assumption, then you have to use a different test, okay? And then finally, we use interval or ratio data. So we essentially are able to identify our null hypothesis, which is that the sample that we obtain, the mean value, is equal to the population value. Okay, so there's no difference there, that's fine. We've covered this before, that shouldn't be surprising. Or we can say that we think there is an effect, but we're not sure whether it's larger or smaller. So we just know it's different, it's not equal to, okay? That's why we have this non-directional alternative hypothesis here. Or we could state directional hypotheses, saying whether we think the sample is larger in this case than the population mean, or in this case, the sample is smaller than the population mean, okay? And we can use either the Z or the T test in order to assess this. So it's fairly straightforward. In order for us to basically make this, in order for us to actually use this statistical test, what we need to do is need to get the sample mean here, x bar, subtract the population mean, and then divide that numerator by the denominator. And the denominator here, as you remember from last week, is the standard error of the mean. And the way that we calculate the standard error of the mean is that we take the standard deviation and we divide it by the square root of the number of samples, okay, for the normal distribution. If you have fewer values than 30 and you're using the t-distribution, then you'll need to make sure you're using the number of degrees of freedom as the denominator in this example. So remember I showed you within R why we need to subtract -1 from the sample size when we've got a small number, and that's because we don't necessarily have the extreme values within our sample, and therefore if we don't, we end up with biased estimators. Okay. So when we run through this, we end up with either the Z or the T statistic. Let's go through an example now. So an energy official claims that the oil output per well in the United States has declined from the 1998 level of 11.1 barrels per day. 50 wells are randomly sampled throughout the US, and a mean output of 10.7 barrels per day is obtained in that sample with a standard deviation of 1.3 barrels. We need to test this claim that oil output per well in the United States has declined at an alpha value of 0.1. Okay, so essentially we want to test this claim. We want to be 90% certain that we're right. We can accept a 10% error margin where we might be wrong. That's the significance level. And we want to run through those 6 steps now in order for us to assess this. So the null hypothesis will be that the mean that we've collected will essentially be the same as the population mean up here, so 11.1 barrels per day. Whereas the alternative hypothesis, and it's a directional hypothesis, is indicative that the mean that we've collected is essentially lower than the population mean. Okay. And then in step 2 here, we use the one-tailed one-sample difference of means using the Z-score. I think that's fairly straightforward. We've used this now already. I've showed you how to do that in the previous example. And then in step 3, we need to identify our significance level, so that's our alpha. Then in step 4, we need to get our Z critical value. So remember, we need to look up in the Z table, or we need to, in R, call we need to use the p-norm function, for example, in order for us to call specify the number, specify the quantile that we want within the distribution, basically. So it provides us with the critical value in terms of the standard deviations that we have. So for example, here what we want is this critical value point down here where we have 10% of the values beneath and 90% of the values above, and the critical value for that is minus 1.28 standard deviations below the mean. Okay, so we've got the mean here at the center of the distribution, and then we have the minus 1.28, which is just down here. It's this line, and it means all the values that land above. So there'll be 90% of the distribution landing above here, okay? And then there'll be 10% of the distribution in this bottom bucket here. So if it lands up here, then we do not reject the null hypothesis, and if it lands down here, then we would be rejecting the null hypothesis and accepting the alternative hypothesis, okay? So how do we do that in reality? Well, to get the Z-score, we need to go back to a formula here. So we need to basically subtract the population mean from the sample mean that we've obtained, and then we need to divide it by the standard deviation divided by the square root of the sample size, which is the standard error of the mean. And when we do that, we get minus 2.18. Now this number, obviously, minus 2.18 is actually below this line here, which indicates that the sample is within our zone of rejection for the null hypothesis, which means that we basically reject the null hypothesis at the 90% confidence level. Okay, so hopefully that's reasonably clear for you. Essentially, we will be able to run through examples of these within the laboratory session. So if it's not clear for you yet, we will be able to go through and specifically demonstrate each one of those steps, what we're doing in order to obtain this result. We can also use proportional tests. So previously we were using the example of means that we've obtained. We can also look at proportions of an overall sample or population. So to actually use the one sample difference of proportions test, we're able to compare that sample proportion to a population proportion using the row value. So essentially we need to make sure that we have random sampling here and that the variable essentially is binary. Okay, and what we end up with as a consequence is a percentage of those samples that fall into each one of those binary outcomes. Okay, so for the null hypothesis here, we're expecting the sample to be equal to, the population proportion to be equal to the sample proportion. The alternative hypothesis is that they are not equal. Obviously, it's the equal sign with the slash down the middle, indicating that they're not equal. And we're not specifying a direction here. So we're not saying whether it's larger or smaller. We're just saying they're different. Okay, so nice and easy. Or we can specifically state that we expect that the proportion that we obtain in our sample is, in this case, larger than the population, or in this case, smaller than the population. Okay, and we're going to use the Z test here. So the way that we do that to get Z is we need to subtract the proportion of the population from the proportion of the sample, divide it by the standard error of the proportion. Okay, so it's fairly simple. We did briefly cover this previously, how to calculate this particular statistic. So let's go through an example of that. So Middletown officials want to know if the proportion of families with one or more children under 18 is different from the national trend. Okay, so we think that here we're not. So they want to know if the proportion of families with one or more children is different from the national trend. So they're just saying it's different. They haven't said yet whether they think it's larger or smaller. It's just indifference. So a random sample is compiled of 250 Middletown families, so that's quite good. That's like quite a reasonable number of samples, particularly if you have to go out and collect that data yourself. 105, so 42% of the families actually had children under 18, okay? And then the last census showed that 48.6% of the families have children under 18, okay? So we have the sample here, and then we have the actual proportion in the whole census, so the population. And then here comes the crux of the question. Is Middletown smaller than the national trend? Okay, so you get the hint that it's directional. Here we think that the sample has a smaller proportion than the national trend. Okay, so the proportion for the null hypothesis will be that our sample is equal to the population, whereas the alternative hypothesis is that our sample will be lower than the national trend. Okay. So we're going to use the one-tailed one-sample difference of proportions using Z. And then essentially we're going to use an alpha value of 0.1 here. So we're willing to accept a 10% error margin, but we also want to be, as a consequence, 90% certain that the conclusion that we reach if we reject the null hypothesis is actually true. Then we need to get our Z critical value. So we can use the Q norm function here in R, which will help produce this value for us. So this here is going to be minus 1.28 standard deviations below the mean here. So we're going to have 90% of our values in this area here where we would not reject the null hypothesis, and then 10% of our values here where we would reject the null hypothesis, okay? And then we can calculate that fairly simply. So we need to subtract the proportion that we've obtained, subtract the population proportion from the value that we obtained in our sample, and then we just need to calculate here the standard error of the proportion, which is slightly more complicated than the previous example. So we basically need to take the proportion we've got here and then subtract it. So we're multiplying it by the complement for the numerator, and then we need to divide it by the denominator, and we take the square root of this. And that provides us, in this particular instance, with a Z value of minus 2.12, which is far below the minus 1.28. So our minus 2.12 is going to be down here in this bottom part of the distribution, okay? Okay, so in step 6 here, we then need to, as a consequence, reject the null hypothesis at the 90% confidence level because we've got this Z value that is below the critical threshold, okay? I hope that's reasonably clear for you. We're going to cover that in much more detail once we get into the laboratory sessions, and you can see how we work this out line by line. There are lots of issues with statistics, and I think the one critical thing that I'm trying to get through to you through this whole course is that there are these tests that we use, there are these statistical approaches that we use, and they all have limitations. And really what I'm trying to do is to prep you so that if you're presented with statistics later in life in your employment workplace, then essentially you can think critically about how they've been produced, what the numbers mean, the implications of, for example, using hypothesis testing, setting your alpha value, and really kind of what that means in terms of probability and where your error margin potentially sits within that data. Okay, so it's not just something that you can just accept at face value. I need you to be able to have a kind of a feeling for the underlying data so that you kind of know the implications of these different tests, because, you know, you can't take these at face value. I think there's that famous quote, which is there's lies, damn lies, and then statistics. But that's not to say that statistics aren't incredibly important and the fundamental basis for scientific discovery. It's just that you need to be aware of what goes into making statistics. And in fact, if you want to read a lot of if you want to look at how statistics can be used badly, and there's lots of examples out there, then you should look at sometimes how they're used within the national media in order to portray one particular political opinion over one particular other political opinion, okay? And there's this kind of murky area in there where the way that people use statistics in kind of ways which statisticians would be a lot more cautious of. I think that's probably the best way that I can put it. Okay, great. Look, we're going to move on now. In those other parts of the lecture, we covered the 6 steps, and then we went through 2 different examples with 2 different tests. And now I'm just going to highlight some of the issues that we have. We're also going to be moving on to thinking about p-values. So we don't necessarily use formalized hypothesis testing in all of the future tests. What we actually use is a p-value, a probability value, which is indicative of carrying out a full hypothesis test, but without going through that entire rigmarole. The reason why we kind of gone through the hypothesis testing approach first is so that you can then later interpret the much more efficient p-value that can be used as a way to indicate whether we think there's significant difference or not between, for example, a sample that we've collected and the population data. Okay, so I think this is all fairly clear for you so far. We'll be moving on to using p-values to determine significance. You should remember that the p-value is equal to the alpha value, so it's the probability of actually obtaining a type 1 error occurring, so that's a false positive. So that's something that we want to be very, very cautious of. We need to be much more cautious of that than making a type 2 error, which is essentially a false negative. Okay, so the probability of getting a calculated Z or T statistic, so exceeding our critical value by chance, exceeding our critical value completely by chance. Okay, that's fine. I mean, we've already discussed this in terms of it being equal to the alpha value. Okay, so yeah, the alpha is arbitrary, whereas the p-value is calculated. Fine. So by using a p-value, you can essentially skip parts. Okay, I've already said this, that we can use this to kind of skip all of those 6 procedures, which I'm going to make you learn because you need to, I'm afraid, learn those 6 steps. But let's just put it this way, professional statisticians will use a p-value and understand what that means, and therefore you can kind of take some shortcuts into how you make decisions. I think the key point there is that if you don't understand that hypothesis testing proportion, then using p-values won't actually provide you with any sort of intuitive understanding. And you know, I think it's daunting as a statistics student at first when you look at a full table of regression statistics with coefficients and all these different metrics, but you kind of need to work from the very simple tests and go slowly to understand what each of the metrics means and all the assumptions that are embodied within them in order for you to kind of really get a grasp for the particular area that you know, can provide you with fantastic job opportunities. So I think this is all fairly straightforward. Yeah, we'll be using in the assignment homework formal hypothesis testing. You might be asking, well, how does p-value testing work? Essentially, if you have a smaller p-value, it indicates the observed statistic is further away from the null hypothesis. Okay, that's fine. So a p-value of 0.05 indicates if the null hypothesis was actually true, there's a 5% chance of drawing the samples being tested completely at random. Okay, so we've covered this before, this type of thinking. I've always tried to emphasize, and actually we did it last week when we were looking at an alpha value of 0.1, and I was showing you where the means may lie, and an alpha value of 0.1 means that for every 1 out of 10 means that you pull, it's going to lie outside of your critical value and potentially give you a false positive completely by random. So you just need to be very much aware that this can take place, okay? Okay, so the thing about the p-value is that if you are over here and you're not below 0.05, then this might be suggestive but inconclusive. You would say that you can't really be 95% sure here that the effect didn't just occur by random. Whereas over here, when you're below the 0.05 level, you can start to be make stronger conclusions because you've got a much smaller probability of the result just occurring completely by random. Okay. But I think, this is one reason why some people don't like classical statistical testing, is that you could publish a paper saying that this effect exists because you've got significant results. But I mean, there's still a 5% chance that your results completely occurred by random, and you need to be very cautious when you interpret these results as a consequence. So how does the p-value in testing work? We can compare the p-value to our hypothesized alpha value. For example, we conduct a test and would reject the null hypothesis when you get any p-value less than 0.1, fine. But you can also use p-values to make more qualitative choices. Okay, so I mean, I don't really... You can, it's kind of indicative. You're in this murky area down here of suggestive but inconclusive results, and so you don't have a significant finding. That's fine. It might suggest there's some sort of effect going on. Maybe you could go out and collect more data and then rethink the question. But ultimately, it's a bit of a murky grey area drawing qualitative conclusions when you're in this area. I mean, pretty standardly, most journals would be expecting you to use some sort of 95% significance level, so an alpha of 0.05. So there wouldn't be a conclusive effect if you were over here. One-tailed testing, the p-value is a probability of getting the calculated statistic, or more extreme. That's fine, we've covered this already. And then the reciprocal of that is that in the two-tailed testing, the p-value is double the probability of getting the value, or more extreme. Okay, remember, because we're working in both tails of the distribution. So I'm going to keep coming back to this just to kind of drill it into you that if it's directional, we're only focusing on one end of the distribution, maybe because we think that the house prices in Fairfax are definitely higher. We're quite sure that they're going to be higher than Virginia State, and therefore we're only going to look at the top end of the distribution. And then compare that to maybe an area where you just started studying, you don't have any a priori knowledge, so no prior knowledge. You might just say, well, the results in the sample, the mean is just going to be different. We don't know whether it's going to be larger or smaller. And that's where you're going to be in your realm of two-tailed testing, okay? So issue 1, because there are many issues with this type of work, I just need to go through them with you. So the null hypothesis is a statement of established thought. Fine, we've kind of covered this already, that the null hypothesis is the business as usual case where there's nothing new, there's nothing significant, there's nothing meaningful, there's no relationship. It's just the kind of starting point, the baseline for all of our statistical testing, okay? Whereas the alternative hypothesis is actually challenging that assertion that we have, or perhaps it's a new point of view, hence why you're researching it, okay? So this is somewhat different from the baseline, the day-to-day assumption as to how the world works. Maybe there's no relationship between these two particular factors, okay? The null hypothesis and the alternative hypothesis should not be formulated based on the data, so this is really key. This is a research integrity issue. Instead, they should be determined before looking at the sample data, okay? Otherwise, this is fishing. It's really incredibly bad academic practice. So before you look at the data, you need to make up your mind as to whether you, as to how you think the null hypothesis and the alternative hypothesis should be formed. And then later on, you are able to judge whether they are right or wrong. The completely wrong and incredibly unethical way to do this is to run all of your tests, look at what's significant, and then basically write the paper based on that result. I mean, that is incredibly bad practice. People lose their jobs over this. People are barred from specific journals if they're caught doing this. Do not do this. This is incredibly bad practice. Not only is it bad for academia, but if there's research funding or if there's money being allocated based on these decisions, then you could be talking about millions or billions of dollars worth of wasted capital as a consequence of this, and that money could be much better invested to make people's lives better in a different way. So issue 2. Are we dealing with a two-sided or a one-sided hypothesis? Which should it be? Well, it depends on the context of the problem, okay? So what I've presented you with today is the very kind of high-level framework. So, maybe you're saying, Ed, this is complicated. You've given me way too much information. But this is kind of the high-level theoretical framework. And then hopefully when we go through it in the lab and you do the assignment, all of the pieces will start to slot into place for you by the time you've also read simultaneously the book chapter. But yes, it means that you do need to be aware of the problem. You've got the framework now. You just need to work out the sensible choices that you need to make in order to make a correct assertion, a correct hypothesis based on the data. Okay, so one-sided is where we have some sort of a priori knowledge as to which direction the effect is going to run, whether house prices will likely be larger in Fairfax because we know it's an attractive place to live, there's lots of jobs, there's good schools, relative to maybe other places in Virginia which don't quite have the same level of, the same economic trajectory of the local economy that Fairfax has. Okay, and then the two-sided test. So we know that there are some issues with this. So it gives you a higher likelihood of making a type 1 error. So the doubling of the p-value. In reality, we generally have an idea of the direction of the hypothesis. Yeah, that's fine. I mean, most of us are going to be going into this research with some sort of expectation as to what the answer, may be in advance, and we collect data and we evaluate that impartially, but we use that a priori knowledge in order for us to identify the hypothesis that we think is correct. Issue 3, using a hypothesis test, always report the p-value for the hypothesis test and make sure that you correctly provide the conclusion based on evaluating those test results. So we say there's strong, moderate, weak, or no evidence against the null hypothesis. This is a fairly standardized way that if you're writing a dissertation and you're interpreting this, you need to make sure you use the language that I'm giving you here in order to report the results, okay? You shouldn't say that we accept the null hypothesis. That's because the null hypothesis is already the status quo, okay? Remember, there's an element of randomness and probability within our statistics. We can never say anything with certainty here. We can only present the conclusions based on the evidence that we have, based on the alpha value that we have, which leads to a certain confidence level in the results. So you need to be careful with how you actually then report the information. Issue 4, there is this issue with the number of degrees of freedom which you have, so this becomes more important in the future tests that we carried out. So you basically can earn a degree of freedom when you collect each data value, but you spend a degree of freedom in estimating a statistical parameter. Okay, so one example might be that you collect journey to work information, and there's an example in the book on this kind of journey to work information that you might be interested in. So if you collect 51 data points for journey to work times for different people, you need to calculate the sample mean for inferential testing of the mean, and the number of degrees of freedom is 51 minus 1, okay? So you've got 50 degrees of freedom. If I haven't already covered this, and I think I did maybe when we were in the laboratory sessions, but the way to think about the number of degrees of freedom is imagine that you have a soccer team and you're the manager, and basically you're going to allocate all of your on-field players first. So you allocate the strikers and then the midfield and then the defence, and then eventually what you end up with is you end up with the goalkeeper at the end. And because the goalkeeper is unable to be allocated to any other position on the field because you've already filled them up, the goalkeeper, as a consequence, doesn't have any degrees of freedom. It has to go into the goalkeeper position because you've only got a certain number of players on the field. Okay, so there's 11 players on the field. So my point here is that the reason why the number of degrees of freedom is 1 minus the sample size is because you've allocated all of the other data points out, and then the last data point that you allocate has to go into that one position. So this is how I think of it. It might kind of be useful for you to think about it in this particular way, but that just gives you a little bit of an explanation as to why we have this n-1 as the number of degrees of freedom, okay? Because that one final sample point that you allocate doesn't have any ability to freedomly to be allocated to any of the other positions. Okay. Issue 5. Parametric versus non-parametric tests. So far we've talked about just the parametric tests. So these are normally distributed data tests. But there are issues, and pretty much all of the testing that I've done in my career, the data that I get back is never parametric, which means you either need to carry out a bunch of transformation tests to make it normally distributed so you can use a parametric test, or you need to look at non-parametric tests, which are basically, in this case, think of it as being distribution free. So they don't require you to have interval or ratio data or certain parameters. So you need to think about the questions you're asking, and you need to think whether they meet the assumptions or not for the particular tests, particularly normality. And if they don't, then you need to think about the other non-parametric tests, which, you know, I haven't covered yet, but we're going to be covering some in the weeks to come, okay? Strategies for the parametric versus non-parametric decision. Well, if the data you have are nominal or ordinal, then you must run the appropriate and non-parametric test, because obviously they can't be normally distributed. If you're completely sure about the parametric assumption being set, then you can just run the appropriate parametric test. But if you're in doubt, then one thing you may want to do is you could downgrade your interval or ratio data so that it becomes ordinal or nominal. Remember, we've covered these data types earlier on in the class. So nominal is categories, ordinal is basically categories where you've got a certain ordering within them, so a kind of hierarchy, and then your interval or ratio data is your classic continuous data forms, okay? But you could downgrade them into categories, okay? So you could, like you have in a histogram, you could put them into buckets, basically, and those buckets, those segments could be ordinal because then they would have a particular set of categorical meanings within the data, okay? And if you're uncertain, you could just run both non-parametric and parametric tests by pairing them. That might provide you with more insight. I will cover within this course the way that you can test your data for normality. So it's the Kolmogorov-Smirnov test, which basically enables you to understand if your data are not normally distributed, so if it's significantly different from a normal distribution. And that's a kind of nice formalized way for you to say, yes, I meet this assumption or not. And I use that in some of my previous master's dissertation work, just basically to demonstrate that I kind of have met this assumption, and therefore it provides a bit more weight to ensuring that your methods are valid and therefore your results are consequentially valid as well. Okay, great. Well, that's the class. I appreciate that you know, there's a lot to go in these lectures, not a lot to go over. What I would say is that, you know, clearly some of you are doing very well on the tests. Then some of you, you know, are still struggling with some of the content. If you are still struggling, then the way to do it obviously is to, you know, put the hours in to make sure that you're going over the work here, going over the labs, reading the actual book multiple times. And then I think, you know, what really helps is if you can kind of revise for this material by kind of putting it into your brain. So for example, for, you know, the central limit theorem, write down those different requirements requirements for the central limit theorem, or go over the hypothesis testing 6 steps, write them down, understand what they mean. Formulating that and revising it in a way will help to really kind of lodge that information in your brain. And then hopefully, because I think we've got 7 weeks left now until the end of the course, that will give you plenty of time to kind of make up any marks that maybe you've lost in the first part. Okay. What I will say is that I'm around. I'm going to be reaching out to some of you just to check if you're okay. I'm going to be going over any issues that you might have, so please don't hesitate to reach out to me. I'll definitely be happy to help you out, and I'd look forward to actually hearing from you. None of us are really enjoying teaching remotely like this, and hopefully by next term we can all be back in the classroom together. Okay, well, thanks a lot for tuning into this lecture, and I look forward to seeing you in the laboratory. Thank you. Goodbye.